How do you prevent mode collapse in VAEs? Imagine trying to create a variety of images or data points, but your model keeps producing the same few outputs. That's what happens when mode collapse occurs in variational autoencoders. It's a common challenge in deep learning and generative AI. Mode collapse happens when the model ignores the latent variables and produces repetitive results. This often ties to something called posterior collapse, where the model's approximate posterior distribution collapses to the prior. This means the latent space stops carrying meaningful information. To prevent this, one effective approach is to balance the two main parts of the VAE loss function, the reconstruction loss and the Kullback-Leibler divergence. The KL divergence helps regularize the latent space, but if it's too strong early on, it can cause the model to ignore the latent variables altogether. Using a technique called KL annealing, where the weight of the KL term is gradually increased during training, allows the model to first learn useful representations before regularization kicks in. Another method involves scaling the mean of the approximate posterior distribution. This encourages the model to use the latent variables more effectively, avoiding degenerate solutions where the model ignores the latent space. Architectural choices also matter a lot. Using more expressive encoder and decoder networks, like residual blocks or convolutional layers, helps the model capture richer latent representations. For example, residual networks improve feature extraction and reconstruction, supporting better utilization of the latent space. Regularization techniques like dropout or adding noise to the latent variables during training can also promote diversity. This prevents the model from collapsing into trivial solutions by encouraging it to explore different latent configurations. Instead of sticking to simple Gaussian distributions, using more flexible options like mixture models of Gaussians can better capture complex data distributions. This flexibility makes it harder for the model to collapse because it can representing a wider variety of data patterns. Early stopping during training and data augmentation are practical tricks too. Early stopping prevents overfitting, which can lead to collapse, while data augmentation increases data diversity, pushing the model to learn more robust latent features. Some researchers also modify the objective function by adding extra regularization terms or combining the VAE with adversarial components like generative adversarial networks. These approaches can improve the quality and diversity of generated outputs, reducing the risk of mode collapse. In real-world applications, like image generation tools or content creation plugins, preventing mode collapse is essential. It ensures that the model produces a wide range of high-quality, varied outputs, which is key for creativity and usefulness. Addressing mode collapse also supports ethical AI use by promoting diversity and reducing repetitive or biased outputs. Overall, a combination of careful regularization, smart architecture choices, and training strategies can keep your variational autoencoder generating diverse, meaningful results instead of falling into the trap of mode collapse.